All right, good afternoon and welcome back to ECE 164. Today we're going to talk about the frequency response of circuits. If you recall last lecture, we talked about this particular circuit and we were posing the thought experiment of how much gain we could make from this circuit. Today we're going to flip that around a little bit and we're going to try to understand how fast the circuit can go. Now, in order for this to be a truly meaningful discussion, we need to be a little bit more realistic about what's actually driving this particular circuit. And so what I've done here is I've added some finite source impedance. So Ri would be the output impedance of whatever was driving this circuit. And so the output impedance could be, for example, the impedance of the sensor. It could be the output impedance of the previous stage. But we need this impedance in order to really have a meaningful discussion here. Okay, so when I ask how fast this circuit can go, really there's two ways of thinking about this. One, we could think about this in the time domain. In the time domain, to assess how fast a circuit was, you would apply a step at the input, and then you would look at the output to see when it settled. The other way of thinking about this is probably what we're more used to, and that's to apply a sinusoidal signal at the input and then look at the output at the gain and the phase. And we could reconstruct essentially what would be a Bode plot if we swept that input frequency. You know, there's no right answer here in terms of which matters more. When we're talking about this, it's very application dependent. And of course, if we know the time domain response, we can estimate the frequency domain response and vice versa. In 164, we're mostly going to talk about the frequency domain response of this and use that to argue the useful range of a circuit. But as I said earlier, there are a whole class of circuits, for example, switched capacitor circuit or discrete time circuits, where you are much more concerned about the step response rather than this other notion of continuous time circuits, where you would be more concerned using kind of the frequency domain analysis of this. Now, when we're talking about the bandwidth, the application really drives what's important in terms of bandwidth. For example, my research, we do a lot of work on biosensors, and biosensors, they typically do not have a lot of bandwidth. When we're talking about biosensors, you're typically often in the millihertz to single digit kind of kilohertz range. Other applications, for example, audio, have very well-defined frequencies, 20 hertz to 20 kilohertz, predominantly driven by the physiology of the ear. Video tends to be a little bit higher in frequency, about 50 megahertz. Cable TV, 1 to 800 megahertz. And then there's a whole slew of radios that have various different frequency ranges. AM, FM is about 100 megahertz. Wireless LAN, cellular phones, GPS. It goes on and on and on. And so the only takeaway, and the reason why I wanted to bring this up, is that you can see the diversity in frequency ranges. You have 5 gigahertz all the way to millihertz. So we essentially have 12 orders of magnitude of frequency response here, and we'll need to know what application we're designing these circuits for. So fundamentally, coming back to our thought experiment, why can't all circuits run infinitely fast? Well, it turns out that in every circuit that we're going to build, there's going to be capacitance, okay? And this capacitance is going to limit how fast the circuit can operate. There are some cases and some applications where you can use inductors in order to effectively cancel out capacitors. That's often done when you're doing what's called resonant circuits. As you'll see many times in 166, you will use resonance, i.e. we're operating in a very narrow frequency range, and so we can resonate out the capacitive effects around a particular frequency. However, if you want broadband, i.e. circuits that operate over a wide frequency range, inductors typically don't work. Furthermore, at very low frequencies, the amount of inductance that you need is often prohibitive to do that. It works well at kind of RF or gigahertz, terahertz frequency, not so well at hertz or hundreds of hertz or kilohertz. So why is it that these capacitors prevent the circuit from running infinitely fast? Well, think about the current that we have in a capacitance. So the current is equal to C times dV dt. And so as dV dt increases, i.e. as we try to run this frequency faster, it requires more and more current, or larger IC. So what this means is that at higher frequency, this capacitor effectively looks like a short, and it requires more and more currents in order to drive it. Okay? Um, the reducing impedance ultimately is what limits the bandwidth of the circuit. And so in order to orient us, let's consider this very simple example. Let's go back to something that we've seen many times. This is an RC low pass filter. Okay? And so here, if I wanted to solve this, I know the current through this capacitor is equal to I times C dV dt. Okay? And I can use the Laplace transform in order to transfer this to the S domain. And so I can write the S domain equivalent of this is equal to S times C times the voltage across this capacitor, Vc of S. Then I can derive the voltage across this capacitor divided by the current. This is simply the impedance of this capacitor, Vc, where it's equal to 1 over Sc. So now I can write a transfer function in the S domain of this simple low pass filter. I'm simply writing V out divided by V in, where this is an impedance divider. Okay? So it's the voltage that I have at the output divided by the sum of these two impedances, or 1 over Sc divided by 1 over Sc plus R. Multiplying by R in this equation gives us this very familiar equation that shows that the transfer function is equal to 1 divided by 1 plus SRC, where we will take this RC and we will define this as a pole. Okay? And so we would say that this circuit has one pole. It's a left half plane pole, which is going to give us a 20 dB per decade frequency roll-off. All right, so if we look at the complex plane here, we're plotting omega on this axis, we're plotting the gain on this axis, and we're operating at right at the real axis on this. And so if we look at what this looks like on the S plane here, we have one left half plane pole. It's on the real axis, and if I was to draw the kind of diagram here, I would say that this is the, if you're used to the tent pole argument, we're essentially creating a pole at this frequency. And so this would prop up the tent that we would otherwise drape over our frequency response. All right, so now if I wanted to consider the magnitude and the phase of this, I would evaluate H of S at S is equal to J omega. And so this would give me the steady state phasor response of the circuit, where if I was to take the magnitude of this, I would simply mathematically get that it was equal to 1 divided by square root of 1 plus omega RC squared. And the phase, which is the arctangent of minus omega R times C. We would often display this or show this using a Bode plot, and on a log-log plot, this would simply be straight lines, okay, where I have, as I said earlier, 20 dB per decade roll-off due to the magnitude response. And so the Bode plot of this, it would look flat, and then it would start to roll off. We can find the exact positioning of this pole by plugging in the pole frequency. So this pole is at 1 over RC, where this is equal to 1. And so if I plug this into the magnitude expression, I get that the magnitude at the pole is equal to 1 divided by root 2, which if I look at the decibel value of that, it's minus 3 dB. And so when we're talking about the 3 dB or the minus 3 dB frequency, this is often where we refer to the bandwidth point as the dominant pole. And so we would say the bandwidth of this particular circuit was 1 over RC, or 1. Okay. Likewise, the phase. So the phase at the pole frequency is equal to the arctangent of -1 or minus 45 degrees. Okay? And so that is that each pole is going to give us a 90-degree phase shift. And right at the pole frequency, we have already lost minus 45 degrees, or half of the phase, and it takes a decade before and a decade after in order to complete this complete phase transition. And so this is oftentimes when you see more experienced analog circuit designers and you ask them to look at the Bode plot and to identify the poles and the zeros, I would say that the most conventional way is to try to look at the magnitude response. That is usually the most comfortable, but more experienced people will dive directly to the phase. Okay, and the reason being is very simple. You get a lot more dynamic range. The 3 dB point is actually rather difficult to pinpoint on this plot, whereas the phase, since it starts an order of magnitude earlier in the frequency response and ends an order of magnitude later, it gives you much more precision in finding exactly where that pole is. So I would encourage you to become very comfortable looking at Bode plots and identifying where the poles and the zeros are, as we'll talk about in just a second. So it turns out that most circuits do not just contain poles, they also contain zeros. The zeros may or may not lie within the bandwidth of interest. Oftentimes they are at higher frequencies and they will relate to, as we'll talk about a little bit later, the non-dominant poles. However, if we look at this circuit, the zeros are quite interesting. And so what I've done here is I've taken the simple RC circuit and I've simply added another resistance. Okay? And the addition of this resistance causes an interesting phenomenon. So here, if we were to write out the impedance divider again, I have on the top the sum of these two impedances, 1 over SC plus R. And when I consider the entire impedance, I have 1 over SC plus R, which when I simplify by multiplying by R, I end up with 1 plus SRC divided by 1 plus 2 SRC. Okay? And so what this says is that in the numerator, I have 1, 0. In the denominator, the root, I have 1 pole. Okay? The pole is at minus 1 over 2 RC, which is a left half plane pole. And the 0 is at minus 1 over RC, which is a left half plane 0. And so when I look at this, if I was to consider only a 0, so let's start off with 1, 0 right on the real axis, okay, at minus 1 over RC. What this literally means for our magnitude plot here is that at that particular point, the magnitude or the transfer function literally goes to 0. Okay, so this is the equivalent of putting a stake in the ground when we're trying to do our frequency overlay here. And now if I was to add a pole and a 0, the pole props up our drape and the tent pins it down at 0. Okay? And so in this example, I have both real pole and 0, or excuse me, 0 and pole on our plot here, where the pole is at minus 1 over 2 RC and the 0 is at minus 1 over RC. And so if I was to look at the Bode plot of this, you would see something that looked like this. So here, previously we had the magnitude response continuing down indefinitely. And so essentially it was rolling off at minus 20 dB per decade forever. However, the addition of the 0 stops this from rolling off further. Okay, and so what happens is we hit the pole, we start to roll off some of the gain, we get to the 0, and then we flatten it back out. And so we had this minus 20 dB per decade, the 0 gives us plus 20 dB per decade, it cancels out, and we end up back here right at a flat frequency response. If we look at the phase, right at the pole here, we are, where are we? Right at the pole's right here. We essentially have minus 45 degrees. We would see this down here. The pole and the 0 are interacting due to how close they are. And so we're starting to lose phase. We don't ever get to kind of this minus 45 degrees. We hit the zero and we start to immediately pick back up the phase that we lost. As you can see, we end up right back in terms of in phase at the input and the output after we get away from kind of an order of magnitude from that zero. Okay. A couple of other important things to remember is that if we look at the transfer function of these circuits, we can never have more zeros than we can poles. We have to have more poles or equal poles than zeros. Okay? And the other thing is that if we look at these circuits, I often get asked, where did the zeros come from and where did the poles come from? I'll try to give you some intuitive insight into that as we go through this lecture. It takes a little bit of practice, but the best way to think about zeros is that oftentimes they provide an alternative path that couples the input and that couples the output. And this will become pretty obvious as we go through a couple of these other examples. It's a little bit less obvious in this example that I derived previously, how to specifically spot that there is a zero. All right, so let's go back to this example that we started off the lecture with, and let's try to understand exactly how fast this circuit can go. Okay? And so what I've done is we're going to construct the small signal model of this. We're going to assume that the transistor is operating in saturation. And to start off, we're going to neglect all of the extrinsic capacitances. So if you recall back from last lecture, when I'm talking about extrinsic versus intrinsic capacitance, I'm really talking about the intrinsic ones that are fundamental to the device operating. In this case, in saturation, that's CGS and only CGS. The extrinsic capacitance, it will add a CGD term up here. We'll see the effect of that in just 1 second. Also, I'm going to assume that R, that I'm loading the circuit with, the load impedance, is much smaller than R naught, such that we can neglect R naught. If you wanted to, you could simply put these two back in parallel, but for simplicity right now, we're going to neglect this. All right, so if I wanted to derive the transfer function, that is how to get from the input here to the output, I would simply do KCL and I see a pretty simple expression. At the input, I have a pole, okay? At the output, I'm simply taking the voltage that I have across this capacitor, across CGS, and multiplying it by GM to get a current, and then dumping it into this resistor to get back a voltage. Okay? And so this can just be reflected in these two transfer functions. At the output, I have minus GM times R, that's this. At the input, I have this RC filter, which is equal to 1 divided by 1 plus SRI times CGS. At this point, it should be very obvious why, at the beginning of the lecture, I insisted that in order to have a meaningful discussion, we needed to include Ri. If we did not have Ri here, essentially Ri was 0, we wouldn't have anything limiting the frequency response because we're driving this with a 0 impedance, which would take away this pole here at the input. All right, so we can simplify this expression a little bit, and oftentimes we try to do this. What we've done here, or I've done, is I've factored out the DC voltage gain, and then I've lumped all of the frequency terms together. And if we look at these terms, it makes it very easy now to identify the poles and the zeros in this. This particular circuit has no zeros, and it has one pole where the pole is at minus 1 over Ri times CGS. All right, so let's do another example, and I actually want to put numbers to it this time so that we can work through the entire example. And so we're going to use the circuit that's on the previous slide, but we're going to have these parameters that VB is equal to 2.5 volts. The transistor is biased with a 500 microamp current. W over L is 20 over 1. 5 kilo ohm load. Input impedance is 50 kilo ohms. And then we're given a whole host of technology parameters. The threshold voltage, the transconductance parameter, the output impedance or the lambda so that we can calculate R out, and then we're given Cox. Okay, and the first thing that we need to do is we need to calculate the input DC voltage such that ID is equal to IB and V out is equal to VB. We also need to calculate CGS and the 3dB frequency. Okay. And so essentially what we're doing is we're working through the DC biasing first, and then we're calculating small signal parameters using those small signal parameters in order to calculate the bandwidth of the circuit. All right, so the input voltage, if we want to bias this transistor with this 500 microamps, we simply need to calculate what VGS is. And so VGS is going to be equal to VT plus this term here, where I'm using this in order to figure out what overdrive voltage I need. And so if I start to plug in numbers into this expression, I need 500 millivolts from VT plus 2IB, which is 1 milliamp, divided by 50 microamp per volt squared, times 20, that's the aspect ratio here, times 1 plus lambda, 0.1 divided by volts, times VB, which was 2.5 volts. Okay, and so this gives me an input voltage of 1.394 volts. I can calculate CGS. Here I'm designing this transistor to be in saturation, given that I used this particular overdrive equation. And so that says that I can also use the same equation when I'm calculating CGS, namely that CGS is 2/3 times WLC aux. Or if I plug in all of the numbers, CGS is about 30.67 femtofarad. All right, lastly, if I wanted to calculate the bandwidth of the circuit, I can use the equation that we derived on the previous slide, that the 3dB bandwidth is 1/2 pi times 1 over the input impedance times CGS. Plugging in numbers, I get that this circuit has a bandwidth of about 103.8 megahertz. All right, so this example was relatively straightforward, mostly because on the previous example, we did not include the intrinsic capacitances. And so what I've done is I've included the intrinsic or the extrinsic capacitances. Namely, I included CGD and I included CDB. CDB is not such a big deal. It's going to create another pole at the output with the combination of these two impedances, R0 and R. The really nasty one here is CGD, okay? CGD makes this very tightly coupled, okay? And so what I did was I did KCL and I massaged this expression as much as I could. And rather than spend 15 to 20 minutes to redo this calculation, I'm simply going to show you the result. Okay? And so here at the bottom, I'm showing V out over Vn. As you might expect, I get some DC gain. So the DC gain of the circuit is still minus GM times R. That should be reassuring given all of our previous analysis of this. We do have a 0 in this transfer function, and the 0 is related to CGD. As I mentioned earlier, anytime you have alternative paths to the output of a circuit, they're likely going to give you a 0. And so if you think about kind of the traditional path or the conventional path that you would have in the circuit, I would take the input, I would develop a voltage across this capacitor CGS, namely VGS. This would then go through this transconductor to turn into a current, and it would get reflected back into a voltage at the output by the output impedance. Okay? What happens with CGD is it lets the signal race forward to the output through this capacitor. And so it provides an alternative path to the output. Importantly here, it has a different phase. So when the signal goes through here and through this GM, we get a 180 degrees phase shift. Okay? When it goes through this CGD capacitor, it essentially starts off with no phase shift. Okay? And depending on the impedance of this capacitor, we can get some phase shift, but it's significantly less than this 180 degrees phase shift that we get going through the transconductor. Okay? And so that's why we have a 0 in this circuit. Now, we have a very big mess in the denominator. But you can see a little bit, and I've tried my best to factor things out and put this as cleanly as possible. But this circuit, even this very simple circuit does not give you a very satisfying result. It's very complicated in terms of its poles. And so what we see is that we have 1 plus s times this plus s squared times this. Okay. What this means is that we have two poles in the circuit. Where exactly these poles are, we cannot tell from when the equation is expressed in this form. We would have to factor this in order to get the exact expression of the poles. And this equation is very hard, if not impossible, to factor into the same kind of simple form that we got previously. Now, what could we do? Well, we could use this expression, and I could go plug it into MATLAB, I could plug it into Excel, and I could plot the frequency response, and I could trace along and find the minus 3 dB bandwidth, or maybe better yet, I could plot the phase and I could find minus 45 degrees and calculate where the pole was. The problem is that this isn't really very useful for hand analysis. If I look at this expression, it's very hard for me to, as a designer, give you much insight. Okay, I can't really tell you if you came back and said the bandwidth is 20, 30% too low. What do I do? I don't know. There's not an easy way looking at this with this kind of high entropy expression to really have much design insight, or more importantly, to know what knobs to turn in order to improve the circuit. And so that's fundamentally what we're going to address right now. And that's how can we fix this such that we can make sense of this. Now, I want to also point out, very often in this class, we're not going to design circuits that are only one transistor. This circuit is incredibly sensitive, or incredibly simple. What happens when we start to add more complexity to this? What happens when we start to add multiple transistors? You can only imagine how difficult these kinds of expressions would be to solve exactly. Okay. All right, so let's look just at the Bode plot of this to try to get a sense of what's going on, and then we can come back in and kind of use some other tricks in order to intuitively reason about this circuit. If you look at when we had the intrinsic cap only, that is when we only considered CGS, we had a circuit that looked something like this, or a response rather that looked something like this. There's a dominant pole, it's somewhere right around here at about 100 megahertz. The bandwidth starts to roll off, it rolls off at about 20 dB per decade. On the other hand, when I plot the frequency response of the previous circuit that we just derived that included those extrinsic capacitors, what we see is a couple important things. One, we see that before we get up to here, it's essentially exactly the same. Okay? It does look like the bandwidth is a little bit lower due to those extrinsic caps. And as we start to roll off, something is going on that's different down here. Okay, so the gain is rolling off at 20 dB per decade, and then you'll start to see over here, all of a sudden it's rolling off a lot more. Okay, and so we'll see what's going on here. This is really due to that non-dominant pole and that zero that are in this second circuit that had the extrinsic capacitors that we didn't see before. Okay. Now, the point that I will make is that these non-dominant poles and zeros, they're not always important. It really depends on the circuit and what we're trying to do with it. Oftentimes, we're much more concerned with what we'll call the dominant pole. The dominant pole is typically what's going to set the bandwidth of the circuit, whereas these, if we're trying to put this in feedback or other things, they're going to determine the phase margin of the circuit. Okay? If we really want to get exact expressions for these, there's really no other way than to deal with those high entropy expressions that I talked about previously. However, if we're more concerned with this dominant pole, we have a couple of tricks that we can do, and I'll walk through those right now. So again, just to remind us of what the difficulty is coming from in this previous circuit, it's not really CDB. CDB is fine. CDB is at the output, it creates a pole with R. That's not the culprit, if you will, for this high entropy expression. It's really CGD, and it's CGD because it's coupling the input and the output of the circuit. Okay? Um, if, for example, we consider the case when CGD was equal to 0, this is a really simple circuit to solve. I simply have a pole at the input, we'll call that tau 1. I have a pole at the output, we'll call that tau 2. And I can just use superposition to put this together, where I have two transfer functions, where V out is equal V out, or V out divided by Vn, the gain, is equal to the transfer function from the input to VGS, that's this first term, and from VGS to V out, that's the second term. It's just these two poles. The first one is a single pole response, so this is 1 divided by 1 plus S Ri CGS, times the gain that I get from this, minus GM times R, and the pole that I get from CdB at the output, 1 plus SR CdB. And so if I wanted to write this in terms of the time constants, this is the DC gain. There's no 0 in the circuit, there's two poles, and I know exactly where these two poles are just by examination without having to write out detailed expressions, okay? And this is the exact response. I've made no approximations here. Where this turns into this very high entropy expression is when we include a finite CGD. All right, so in order to deal with this CGD, let's take a step back and let's look at what's called Miller's theorem. So Miller's theorem is a way of dealing with impedances that may be strapped across two nodes. And what Miller's theorem lets us do is it takes this equivalent impedance and convert it to two grounded impedances. Okay, so an impedance at the input that's grounded and an impedance at the output that's grounded. Notably, in this particular example, we need to know what the gain is. That is, I need to know what V2 divided by V1 is. Okay? What Miller's theorem says is that if I know the gain of this, I can simply reflect this impedance in feedback Z at the input as Z divided by 1 minus K, and at the output as Z times K divided by K minus 1. Okay? And so this is a really powerful theorem because what it's going to let us do is it's going to let us deal with that pesky capacitor that's coupling the input and the output. Okay? As a quick aside, if you're not familiar with Miller's theorem, it's actually a pretty easy thing to prove. The easiest way to prove Miller's theorem is to mathematically show that if I had this particular circuit where Z was in feedback and I had V1 and V2, you can show that it's equivalent to this network. Okay, and so what I've done here is I simply took V1, I connected Z, and I now have a voltage dependent voltage source where this voltage is equal to V2. On the opposite side, on the output, I have Z, and I have a voltage dependent voltage source that is equal to V1. Okay? A little bit of algebra will show us that I can take this from a Thevenin equivalent circuit and transform it into a Norton equivalent circuit. I'm going to do that on both the input and the output. Once I have these two expressions, then I can start to simplify the expression given that this now depends on V1 only. And so anytime I have a dependent voltage source that dependent on the voltage that's applied to its terminals, I can simplify that to just minus the impedance. And so I have minus ZK at the input and minus KZ at the output. And now I have two impedances in parallel. I can simply combine them together and I get the expression that we proved on the previous slide. All right, so let's use this Miller's theorem and let's use a couple of examples. So the impedance of a capacitor, we know that the impedance is 1 over SC, and so I'm going to take a capacitor that's in feedback and I'm going to reflect it at the input and I'm going to reflect it at the output to its grounded equivalence. Okay? And so if I do Z divided by 1 minus K, where Z is 1 over SC, I find that the input capacitance is going to be 1 divided by SC1 minus K, and the output is going to be Z divided by 1 minus 1 over K, which is 1 divided by SC times 1 minus 1 over K. Okay? And so effectively what that means is that when I put this circuit back together, I have a capacitance at the input that is equal to C times 1 minus K, where K is the gain, and a capacitor at the output that is equal to C times 1 minus 1 over K. And so now let's look at a couple of different examples where I'm going to change K. I'm going to apply different amounts of gain to the circuit. All right, so let's start off with the very simple case. Let's say that I have K is equal to 0. And so what do I mean, practically in the circuit? It means that I can wiggle the input all I want, and the output does not change. Okay? Typically this is not a very useful amplifier when I have K is equal to 0, because it's not really amplifying anything. Okay? And so what this effectively means is that the capacitance that I see at the input is going to be equal to C times 1 minus 0, 1 minus the gain, which is just C. Okay? Looking back at the other side, remember that I wiggle this and I'm trying to see or what capacitance I feel. When I talk about feeling a capacitance, you could essentially think of this whole thing as being in a black box, and the only way that you would feel what the impedance was is if you're applying a voltage, you would measure the current. Okay? And in this particular case, what happens is I wiggle the output, and the input, since the gain is 0, doesn't change. Okay? And so I keep wiggling the output. The gain's not changing. I wiggle it more, and the gain is not changing. And so if I was to calculate what effective impedance that looks like, it looks like an infinite impedance. Okay? It effectively looks like an open circuit. I'm wiggling the capacitance. There's no current that's going back into this device. Okay? All right, so now let's work through the case when we have the gain is equal to positive 1. Okay? So I wiggle the input. The output is now copying exactly what I'm applying at the input, right? So think about putting a voltage follower below this. The input, the output, they're identical, okay? If the input and the output are identical, it means that there's no current that is going to flow across this capacitor. Doesn't matter if I'm looking from the input side or I'm looking from the output side, effectively no current. Mathematically, what this means is that when I look at the capacitance, it looks like there's no capacitance there. I get 0 on both sides. All right, let's now consider the case when I have K is equal to 1/2. And so what this effectively means is that I have a gain of less than 1. So when I wiggle the input, the output wiggles in phase, but it only wiggles half as much. Okay? And so when I look from the input side, what this means is that I am going to be supplying current, okay? But the capacitance is going to effectively look a little bit smaller than in previous cases, especially when the output wasn't moving. Okay? Oddly enough, something funny is going to happen when I'm looking the other direction though. That is, when I'm at the output and I start wiggling the output, the input is going to wiggle twice as much, okay, by virtue of the fact that I have gain is equal to 1/2. And so effectively what that means is that rather than having the current flow into the circuit as I would expect for a positive impedance, the current is actually going to flow back out at me. This is where we get this idea of a negative impedance. Okay? And so putting this together for the capacitances at the input, by virtue of the output wiggling, it effectively looks like a smaller capacitance. It looks like 1/2 C rather than the full capacitance. And at the output, I end up seeing the entire capacitance here, C, and more importantly, it looks negative. Okay, and this negative sign simply happens because the current is flowing in the opposite direction. All right, so what happens if I actually have positive gain? Now I wiggle the input, the output wiggles twice as much, still in phase. When I look at the input and I apply a voltage, Since the voltage is larger at the output, that means that current is coming back at me, just like in the previous case at the output, which gives rise to this negative capacitance. Okay. At the output, I apply a voltage. The input now is smaller, and so the current is still flowing into the circuit, and I get this partially bootstrapped capacitance at the output. All right, but neither of these cases is, I would say, the more common case, and certainly neither applies to our common source amplifier in particular because the common source amplifier has an inversion. And so it has this phase shift. And so what happens when we have -2? And so here, I wiggle the input. The output is twice as large, but more importantly, it's 180 degrees out of phase. Okay, that's another way of saying that there's a negative sign in front of this. There's a 180 degrees phase shift. So importantly, when I wiggle this up, the voltage across this capacitor is actually significantly larger. Okay, and so in part because if I wiggle this up V1 at the output, it is going down by this gain of 2, and so that means that there's 3 V1 that is dropped across this capacitor. And so this is really what's known as the Miller effect, is that I'm multiplying this capacitor and making it effectively look much larger than it really is. And so rather than this capacitor looking like C, due to the negative, or the gain that being negative, I see much larger capacitance. I see 3 times the capacitance. At the output, similar story, although to a lesser degree, because of how it works here, in the sense that I wiggle this, the input is wiggling, albeit less, and importantly, again, the phase is 180 degrees out of phase, and so I end up with 1.5 times C. Okay. So this is exactly what we have in our common source amplifier, and the one thing that I will mention is that this K, as we've done in all of our analysis for the last few slides, we assumed that K was constant, that K was independent of frequency. It turns out that K is usually not independent of frequency, and so if we want to be precise about this, we need to calculate what K is. So let's look at K for our circuit. And so if you recall, there was some additional circuits over here, essentially a resistance and a capacitance. Those are unimportant in order to find K, okay? And so if we just consider this portion of the circuit, and I was to do KCL at this node, I would essentially get that the transfer function from VGS to the output was equal to minus GM times RL. This is the DC gain. And then I have 1, 0 at CGD divided by GM, and I have 1 pole at RL plus CGD plus CDB. And so if I wanted to really apply Miller's theorem, I would take CGD, reflect it to the input, and then multiply it by 1 minus K of S, where K is now frequency dependent. I would do the same thing at the output, where I reflected CGD that was here to a grounded impedance at the output of magnitude 1 minus 1 over K of S. And K of S is this entire expression. Importantly, as I said earlier, this has 1, 0, it has 1 pole, and it's pretty reasonable to argue that if I have to use this full expression, I really haven't gained much by trying to apply Miller's theorem. I would have probably been better off just using the KCL analysis that we did earlier on and running it through. Okay? And so the real value of using Miller's theorem comes when we can use what's called Miller's approximation. Miller's approximation states that as long as the frequency that we are looking at is less than the 0 frequency, and the frequency that we're looking at is less than the pole frequency, okay, which we happen to know because we just calculated, then it's okay to approximate this frequency-dependent gain term as a constant, okay? And a constant is simply the low frequency gain, okay? So this is known as Miller's approximation. And you will often hear people say Miller's theorem, and they will use this approximation without realizing it. Okay, so really these are two separate things. Miller's theorem is, as I showed you mathematically, it's a theorem, it's provable. Miller's approximation is a handy approximation that we are often going to use in conjunction with Miller's theorem in order to make it actually tractable. Okay. All right, so let's go back to our example. And if we were to now use the low frequency gain, where we had minus GM times R, you can see that we are going to Miller multiply this CGD capacitance. And at the output, it's going to be a little bit larger than 1, but it's 1 over GMR, so it's not much. Okay. This is relatively straightforward to analyze now because I have two independent poles. I have a pole at the input due to this Ri and the combination of these two caps. And I have a pole at the output due to the output impedance and the combination of these two capacitances. And so I can put these together into the two poles that I'm listing here. And as we showed earlier, the dominant pole is typically going to be the input pole. It's a little bit dependent on the circuit, and I'll talk about that a little bit later on. And our non-dominant pole, or the higher frequency pole, is going to be P2 at the output. Okay. And so if we look back at these expressions that I was talking about earlier, we do meet the criteria that omega P2 is beyond omega P1, okay? And so that means that when we're talking about omega P2, and I've used Miller's approximation, I cannot accurately calculate omega P2. Miller's approximation can only be used to calculate the dominant pole because that's the only place that the gain is correct. After that, the gain starts to roll off due to this pole, and the gain that we are quote unquote using to calculate omega P2 is no longer correct. And so we have to discard this result. We cannot use this, it is incorrect. All right. The question of whether or not these conditions are met between the poles and the zeros, it really depends on the circuit parameters that we're using and how we're applying this within the circuit. I will say that in general, omega P1 is typically going to be at the input, and in the example conditions that I gave, that is true. However, there are times when it can be at the output, and I'll walk through a few examples of that in just a minute. But in our particular conditions, if we were to plug in all of these numbers and check these inequalities, we would find that it is met, that omega P1 is lower than omega P2, and that it's lower than the zero frequency. And that's simply to say that we hit the dominant pole first. All right, so how does this do relative to actually simulating the circuit in SPICE? If we plug in all of these numbers, we would estimate the minus 3 dB frequency at 31.6 megahertz. And if you recall earlier in the presentation, I showed you that the actual simulated frequency was 32 megahertz. Okay? And so this is a very good match in terms of hand calculations to simulation values, given the limited effort that we put in to get there. And so let me revisit for just a minute this idea of the dominant pole and what's really happening to these non-dominant poles, and in particular, why we can't use the Miller's approximation. If we look at what's happening, there's an effect that's going on here in the circuit, and it's called pole splitting. Okay? Pole splitting is really that this CGD is bringing in the dominant pole T1, okay, and both techniques are correctly realizing that. So the exact solution gets that right, and this single dominant pole approximation gets that right. Okay. The problem is in this non-dominant pole. Okay, so the exact solution says that the non-dominant pole is pushed out in frequency. That means that it's increased in frequency. This is where it gets the name of pole splitting, is it's pushing the poles farther apart. However, if we were to continue to try to use the result we just got from Miller's theorem and Miller's approximation, it's bringing the pole in. Okay? And this is really because if you look at what's happening here, when we add this additional capacitance, it just adds right on to CDB, And so it brings the pole in, and it gives us this, what I'll call false results. Okay. Um, this is entirely due to the fact that the gain that we are using here is incorrect. When we get to the non-dominant pole, omega p2, the gain is no longer minus gm times r. This has caused the gain to start rolling off, and that's where we're getting this false result from. Okay, so remember, we cannot use Miller's theorem and Miller's approximation in order to calculate the non-dominant poles of a circuit. So why would we want to use this? What is Miller's theorem and Miller's approximation good for? It's a great tool in order to estimate the bandwidth of the amplifier. Okay? It requires very little calculations. It can be done on the back of the envelope. It's useful in that sense, but it's not a replacement for rigorous analysis. In part, it did not tell us about these other poles, and once we do this grounded impedance at the input and grounded impedance at the output, we've entirely lost any notion of the zeros. Even looking back at that circuit, you would not even think there was a zero. Okay? And so that's where rigorous analysis will always help us. It's always important to remember that the approximation is only useful as long as the dominant pole is really at the input. Okay? And this is almost always the case when you have a large input impedance and there's not a large capacitance attached to the output. Okay? If we have a large capacitance at the output, we could actually have the dominant pole at the output. And so you might find yourself asking, well, how do I know how to proceed then? You would typically start by assuming that the conditions that we established on the previous slides are met, and then come back and check that your dominant pole is in the right location, and that it's not near the other poles or the zero, such that K of S can be treated as a constant. After you've done this a few times, it'll kind of become natural, and you'll be able to more or less do this by inspection. Okay, which is really where it becomes much more powerful as just a back of the envelope analysis. And so you might be finding yourself saying, well, geez, this was a great technique for a common source amplifier, but what about other circuits? What about common gate? What about common drain? We're going to learn about those later on in the course. Wouldn't it be nice to have techniques that worked for other types of amplifiers? And it turns out that there is a technique. It's known as zero value time constants. It allows you to do very quick calculations, similar to what we did with the Miller's theorem and Miller's approximation, but it's much more general purpose. Okay, and so what I'm going to do is first walk through kind of the mathematical underpinnings and derivation of this, and then we'll apply it to our common source, and we'll see it in action in just a second. All right, so coming back to our common source amplifier that has this very high entropy expression. Okay, this is what I solved for 30 minutes ago. We can simplify this down into kind of this canonical form, where I have the gain term that is independent of the frequency, and then the numerator I factored to get all of the zeros, and the denominator, ideally I would like to factor it like the numerator, but it turns out that I can't always factor it. Sometimes they just are unfactorable. And so I'll leave it in this kind of long expression of 1 plus B1S plus B2S squared. If we come back to the amplifier, we know that the circuit has a dominant pole. Okay, and this dominant pole is what's setting the minus 3 dB bandwidth. We also know that the non-dominant pole and the zero are really not influencing this minus 3 dB bandwidth. And so if I'm only concerned with the bandwidth, can I come up with an approximation that's much simpler that gives me this bandwidth without having to worry about what's going on up at this higher frequency? Okay. And so if indeed we are only concerned with the low frequency poles, it really means that the effect of this zero we can take out of this expression. And so I can approximate this transfer function as if the zero was not there. Now I know that there's two poles, and I'm going to use the fact that one of the poles is at least 10x higher in frequency than the other pole. And so this is the condition that we'll call a dominant pole in the circuit. And this dominant pole is the one that's going to set the minus 3 dB frequency. The reason why this matters is if I was able to factor this, I would get a expression that looks something like this, where I had 1 minus s over p1 times 1 minus s over p2. And if I multiply that out, I would see this kind of form. Okay? Now, knowing that p2 is 10x beyond p1, I can take this term and I can throw it away. Okay, and so I can simplify this to just look at this term. Okay, and so our simplified expression, we've now tossed away the zero and we've thrown away the second pole, is simply the DC gain divided by 1 minus s over p1 plus s squared divided by p1 times p2. All right, so now if I was to take this expression and I was to compare these two, I can map them back into the poles by the coefficients in this expression. And so I would find that P1 was approximately 1 or negative 1 over B1, and P2 was 1 divided by P1 times B2, or negative B1 divided by B2. Okay? And so if I only want to estimate the minus 3 dB bandwidth, what this means is that all that I need to know is B1. Okay, and so if I can come up with a technique that estimates B1, then I can simply approximate the 3 dB bandwidth as simply 1 over B1. So let's look back at the circuit that we've been analyzing, and let's consider what B1 is in this circuit. So B1 is this S term, and so it's this entire expression here. That's B1. Okay? And if I was to multiply this out and kind of group the terms together in terms of just R times C, what you would find is that it's R times CDB plus R times CGD plus RI times CGS plus 1 plus GMR times RI times CGD. This should start to look familiar. Okay, if you recall back from Miller's theorem, this is essentially taking CGD and multiplying it by 1 plus the gain. Okay? And that's where it's getting multiplied by the input impedance. And so really what's happening is that we're seeing this kind of pop back into this expression. And so if I was to plug in numbers from our example that we've been using and calculate time constants, and when I say time constants, it's really that anytime I multiply a resistance by a capacitance, I'm going to get the unit seconds. It's a time constant. And so I would get that B1 was equal to 5.1 nanoseconds. And 1 over 2 pi times 1 over 5 nanoseconds would give me a bandwidth of 30.9 megahertz. Okay? And so you recall, Spice said 32 megahertz. Miller's theorem and Miller's approximation gave us 31.4. We're only slightly under here with 30.9, telling us that there's a marginal error in disregarding the zero and the non-dominant pole in this circuit. All right, so let me give you a prescriptive method in order to solve for B1 and only B1 without having to solve for the complete transfer function. We're going to first condition the circuit. And when I say condition the circuit, what I mean is that we're taking away all of the low frequency capacitors, things like AC coupling capacitors, DC or decoupling capacitors, capacitors that would give rise to the ability to couple the signal onto the circuit. Okay? Then we're going to short independent voltage sources and open independent current sources. So this is the same kind of methodology that we do anytime we're doing small signal analysis. Okay? And it's important to remember, poles and zeros are a small signal construct. There is no such notion as a large signal, pole or zero. Okay? All right, so once we have conditioned our circuit, we're going to remove all but one capacitor, calculate the resistance seen by that capacitor, and then compute a time constant, where the time constant is R times C. We're going to repeat this for every one of the capacitors that we have in the circuit, and then B1 is going to be equal to the sum of these time constants, and the 3 dB bandwidth is simply 1 over B1, which is 1 over the sum of the time constants. All right, so let's put this into action. Let's try this on our common source amplifier. So this is our circuit, okay, and I've conditioned it. I condition it by shorting VI, and that's all that I need to do in the circuit. All of the other capacitors are important to the high frequency response. They don't have AC coupling type behavior. All right, so now I'm going to start with CGS. If I remove CGS and I look and I find what impedance I see in this, the impedance that I see here is simply Ri. Okay? And so I would say that the time constant is equal to Ri times CGS. Now moving on to the second capacitor, CGD. So CGD in the circuit, I cannot quite just do this by inspection. So I have to apply a test current source and find the voltage, or alternatively apply a test voltage and find the returning current. Okay. In this particular example, I'm going to apply a current in particular because the currents will turn into VGS, which will allow me to pretty quickly calculate what the voltage is over here. All right, so if I do this, I can calculate R2. That is the impedance that this sees is simply VT divided by IT. Okay, and the voltage that I'm going to see is that essentially if I do KVL around this loop, I will see VGS here plus RL, so that's this load resistance times GM VGS, that's the amount of current that I have here, plus this current, IT. Okay, and so this is all divided by IT, and if I massage this expression and factor things out, I get that R2 is equal to Ri plus R plus GM times R times Ri. Okay. Putting this together into the time constant, it's this impedance that we just found times CGD. Okay. Now, it turns out that we're going to see this enough times that it's probably worth remembering this little shortcut. Okay, and the shortcut is that anytime I have CGD, and importantly, I have a grounded source node, okay, I can simply find the impedance looking left, the impedance looking right, and the total impedance of CGD is going to be R left plus R right plus GM times R left times R right, or the sum plus the product times GM. Remember, this only works though if the source is grounded. If we have an impedance there, as you saw in homework 2, this causes a form of feedback, and this expression will not work. All right, and so the last time constant is at the output. The output impedance is R, this capacitance is CdB, so the time constant is simply R times CdB. If we then add up all of the time constants, we get this expression, okay? And we compute an estimate of the minus 3 dB frequency as 1 over the sum of these time constants. And if we go through this, this is exactly the same as what we derived previously. All right, so why do we like this? What are some of the advantages? Well, one, this is a really straightforward way to find the 3 dB frequency of a circuit. On a few slides with very few calculations, we were able to very quickly calculate the bandwidth of the circuit, whereas if we did the full nodal analysis of this, it was a quite exhaustive approach. Okay. More importantly, and where I think the true power of this technique really lies, in that we can figure out what knobs to turn if we wanted to increase the bandwidth. So, for example, here, if I wanted to increase the bandwidth, I know exactly which time constant is the limiting time constant. And I can go in and address that time constant specifically. This exactly tells me which knobs to turn in order to increase the bandwidth, rather than having to try to turn all of these knobs simultaneously. However, there are a couple of caveats, and I think that it's always important to remember some of the assumptions that we made. One of which is that we assumed that the circuit has a dominant pole. When we did this analysis, even going back to very early on in the calculations, we assumed that there was only one pole and that it was a dominant pole, that the other pole was 10x farther away, and that's how we were able to discard that 1 over P2 term. Okay. Second, we very quickly discarded the zero. And so the assumption here is that the zero is at a higher frequency than the dominant pole and that it has no impact on the bandwidth. Okay. One of the biggest mistakes that I see students make is that they assume that all of these time constants that they've calculated are the poles in the circuit. These time constants are not poles. In simple circuits that don't have any coupling, they can be the poles, but in general, they are not the poles. Okay? And the simplest way to even see this from this example is that we know that the circuit has 1, 0, and 2 poles. And yet here, we have 3 time constants. So there's a mismatch between number of poles and time constants. These time constants are not the poles. The time constants are simply, the sum of the time constants are simply equal to B1. All right, so there are times when some of our assumptions that we made in doing the ZVTC analysis may not be precisely met, okay? And I'll give you an example. If the two poles aren't an order of magnitude apart, i.e. that the non-dominant pole isn't 10x away from the dominant pole, you might question whether or not we can still use ZVTCs, okay? Let me show you an example in just a second where the two poles are, at a worst case, they're right on top of each other, okay? And we'll start to understand what the error is and what this causes. The other thing to remember is that the very first step when we were doing ZVTCs was to condition the circuit. And conditioning the circuit meant that we had to get rid of AC coupling capacitors and bypass capacitors. This is critical because these capacitors are meant to be shorts when we're doing the bandwidth analysis at high frequencies, and they do not contribute to the bandwidth. If we were to accidentally leave one of these capacitors in, it would give rise to another time constant, which would incorrectly calculate the bandwidth. Okay, so it's important that we make sure that we've properly conditioned the circuit. All right, and so now I'll do that example that I was just mentioning before of what happens if I have multiple poles of similar or the same frequency. Okay. All right, so let's take this example. Let's say that we had a circuit that had an input impedance of R, or a driving impedance of R, and the input capacitance was C, and the output impedance was R, and it was driving a capacitance of C. Okay. And so this may seem somewhat like a contrived example, but it turns out that this can actually happen pretty often. Take a very simple example of an amplifier that looks something like this. Okay. And if I was to want to increase the gain of this by adding more stages, I could simply add more stages. And what I would find is that the impedance looking into this one was C, the impedance looking into this one was C, and if I continue this on, all of these amplifiers have an output impedance of R and an input impedance of R, and additionally, they also have input and output capacitances of C. Okay? And so if I am simply cascading amplifiers, this case can actually happen quite frequently. And so if I do the exact analysis in order to find the minus 3 dB frequency, the circuit has a DC gain of minus GM times R, and then it has two poles, where the poles are both located at 1 over R times C. Okay? And so if I wanted to find the 3 dB bandwidth, I would find the magnitude of the gain when it was equal to 1 over root 2, and I would get that the minus 3 dB bandwidth was equal to 0.64 times 1 over RC. Okay, so another way of saying that it's 64% of the pole frequency. Rather than having the 3 dB bandwidth be equal to 1 over RC, having two poles there pulls in the bandwidth by 36%, and my new bandwidth is 64% of RC. Okay, now what if I was to use the ZVTCs? ZVTCs, I would say that there's a time constant at the input, a time constant at the output, both of which are equal to RC. Okay, and so I would get that the 3 dB bandwidth was simply equal to 0.5 divided by RC. So clearly, this is not the same answer that we previously got, but let's calculate the percent error so that we understand how bad or how good this calculation is. And so the percent error is equal to the bandwidth that I calculated minus the previous divided by the actual. Okay, and so this gives me a 22% error in the poles. Importantly, it is negative, and so that means that it's conservative. Okay, so again, this is typically where ZVTCs is a good technique, is that it underestimates the actual bandwidth. The actual bandwidth of the circuit is 0.64 divided by RC. Using ZVTCs, even in the absolute worst case, when there's two poles right on top of each other, we estimate 0.5 divided by RC, which is a 22% error. Okay? And so what this says is that ZVTCs are a pretty powerful technique to very quickly estimate the bandwidth, and very importantly, it's a conservative bandwidth estimate, as the actual bandwidth will almost always be higher than this. So with that, we're going to continue on next lecture, and we're going to start talking about common gate and common drain amplifiers, and then we'll also extend the frequency analysis to those stages as well. Thank you.